haven't tuned into the cookery program by mistake, this is M101. It's the first program for Block 5 on mathematical modelling. We're going to illustrate the process of mathematical modelling by looking at the problem of how long it takes to cook a turkey. I have a 20-pound turkey to cook for 1 o'clock lunch. It's been thoroughly defrosted so that it's now at room temperature. The oven's on and it's heated up to 175 degrees centigrade. That's 350 degrees Fahrenheit. So, when should I put the turkey in? Well, I suppose the obvious thing to do is to look this question up in a cookery book. But the difficulty with that is we've got lots of cookery books in our kitchen, and they all give different answers. Here's one cookery book. Let's see what it says. 2 to 2.5 hours for a 6 to 8 pound turkey, 2.5 to 2 3/4 hours for an 8 to 10 pound one, 3 3/4 to 4 hours for an 18 to 20 pound turkey. So according to this cookery book, it's going to take about 4 hours. This one also gives a table, but it doesn't give the same answer. For a 17 to 20 pound bird, the cooking time it gives is 4 3/4 to 5 1/4 hours. That's over an hour longer than the other book gives. Well, I'm going to try one more book to see if I can resolve this discrepancy. This book approaches the question in a different way. It gives the following rules. If the turkey is under 14 pounds, allow 15 minutes per pound, and if over 14 pounds, allow 12 minutes per pound. That's a bit ambiguous. Presumably what it means is that for a turkey of over 14 pounds, you allow 14 times 15 minutes, plus 12 minutes for each additional pound. On this basis, my 20-pound turkey is going to take 14 times 15 minutes, that's 210 minutes, plus an additional 6 times 12 minutes, that's another 72, making 282 minutes. Well, that's about 4 3/4 hours, isn't it? So, there's quite a discrepancy between all these figures. But the average time seems to be around 4.5 hours. Since it's nearly 8:30 now, I better put the turkey in the oven straight away if I want it to be ready by 1 o'clock. Right. All these investigations of different cookery books leave me with one question that I'd really like to know the answer to. Just how are these cooking times arrived at? Is it tradition, trial and error, or is there some more systematic way of finding the answer? So the question is, how can you derive a rule which can be used to calculate the cooking time of any given turkey? In other words, I'm thinking of the cooking time as being given by a function, and I'd like to know how this function is arrived at. Since what we have to find is a function, there's a fair chance that mathematics is going to play a part in solving the problem. But there's a little way to go yet before we can finally resort to mathematics. And that's typical of a mathematical modelling problem. Actually, in this program, we're most interested in the modelling process itself. Cooking turkeys is just one of many topics we could have chosen to illustrate the process. After all, we're trying to teach modelling and not cookery. Right then, let's do some mathematical modelling.
So we want to model the cooking of a turkey with the aim of finding its cooking time. How could we go about that? Now, any problem in real life is going to have lots of different aspects. Some are essential, others more peripheral. In constructing what we call a model of the situation, we concentrate on the features which are particularly relevant to what we're trying to do. What are those features? To find out, we can start by writing down the reason why we need to cook the turkey. I'd say there were 2 reasons for cooking the turkey. One reason is to make it pleasant to eat. But there's another consideration which is probably more important. Killing off the harmful bacteria which are present in raw turkey. Now, bacteria are wiped out by sufficient heat. In fact, experiments have shown that they're finished off if exposed for just 1 second to a temperature of 85 degrees centigrade. So to kill the bacteria, we've got to get the bird up to that temperature. And that's how we'll define the cooking time. It's the time it takes from the moment the bird is put into the oven to the moment when the coolest part of the bird reaches 85 degrees centigrade. And we'll assume that initially, as the bird enters the oven, it's at room temperature throughout, say 18 degrees centigrade. Now that's what we'll consider the objective of cooking the turkey to be, but to set up our model, we need to consider how it happens. By what mechanism is the temperature of the turkey increased to this safe value? It's a consequence of heat conduction. Heat gradually percolates through to the interior after the turkey's been put into the oven, with the outer parts always being hotter than the inner parts. The speed of this process depends on two different things. There's the oven temperature and the turkey's dimensions and consistency. How does the oven temperature affect the speed of cooking? Well, the hotter the oven, the faster the interior of the turkey will heat up. Since Mike Crampin is trying to cook his turkey at 350 degrees Fahrenheit, that's about 177 degrees centigrade, we'll assume that the oven temperature is fixed at this level. Now for the turkey's dimensions and consistency. There are various possible measures of the turkey's size which may be relevant, such as its weight, volume, length from end to end, and surface area. Its shape could be important too. Now we're going to assume that the shapes of all turkeys are geometrically similar, which means that each bird is considered to be a precisely scaled version of any other. And we'll also assume that they're all of the same average consistency. This means that each of the bird's vital statistics, volume, length, surface area, and so on, will be determined by the weight alone. So now I've simplified the situation by concentrating on particular features and making some plausible assumptions. And I'm left with just two major factors: cooking time and weight. Both of these are variables. That is, they're quantities which can be measured. I'll represent each of them by a symbol and specify some appropriate units. So T is the cooking time in minutes, and W is the weight in pounds. Now what? I've written down some variables. The next step is to find how those variables are related. I expect that the cooking time will depend on the weight. In other words, I'll be looking for a function, f, such that T equals f of W. And there's one thing I know about this function: it ought to be increasing. Bigger birds should need cooking for longer than smaller ones. So how can I obtain more information about this mystery function? There are two possible approaches. One is to consider the situation from a theoretical point of view, using the mathematical theory of heat conduction. Well, that theory goes beyond the scope of M101, so we opted for the alternative approach, performing an experiment. Anne Walton did it for us.
A little while ago, I carried out an experiment to investigate the cooking time of turkeys. I did the obvious thing and got some turkeys of different weights and cooked them, one at a time, to see how long it would take. The experiment started with a dozen frozen turkeys from the local supermarket. Their weights ranged between about £5 and £25. Of course, the first thing I had to do was to make sure each turkey was thoroughly defrosted before being cooked. I did that by keeping each turkey in the fridge for several days before it was needed. This turkey was defrosted, so the next stage was to put in the stuffing. Most cookery books give the time for cooking a stuffed turkey of given weight, so to make our experiment comparable, I decided to do the same. To measure the turkey's internal temperature, I used a thermocouple. This was more convenient than an ordinary meat thermometer because it could be hooked up to a meter to give a continuous temperature reading. I decided to insert it between the thigh and the body, as this is the last part of the turkey to be cooked. In fact, this was the second turkey out of the 12. The first one had been cooking for some time. The plan was to keep it cooking until the internal temperature reached 85 degrees. When that happened, a buzzer would sound and the oven would turn itself off. I cooked all the turkeys using that technique, and here are the results. They're arranged in weight order rather than order of cooking. I've also plotted the weights and the times on this graph, and you can see that the weight range goes from just over 5 pounds to just under 25 pounds, and the time range is just over 100 minutes up to 300 minutes. That's 5 hours. In fact, the points seem to lie almost on a straight line. And indeed, that's the sort of relation you do tend to find in cookery books. So what's the straight line which fits these points? And what's its equation? Well, I've programmed the computer to work out the best straight line for these points. Here it is. It doesn't look too bad a fit at all. And we can also find its equation from the computer. It's T equals 9.4W plus 70. And we could use this equation to work out the cooking time for a turkey of any given weight. But is that the whole story? Here's that line on our graph, but now we've extended it all the way back to the t-axis. And now perhaps it doesn't look quite so good. In fact, if we imagine turkeys of smaller and smaller weight, we'd expect their cooking time to approach 0. This straight line certainly doesn't do that. It's trying to tell us that it takes 70 minutes to cook a turkey of 0 weight. And that's absurd. Well, a turkey of 0 weight is also absurd, but this kind of thought experiment does suggest that our model could be improved. The conclusion of the thought experiment is that points should lie on a curve that slopes down to the origin. Does the data bear this interpretation? Well, I can test that quickly using the computer. I won't get it to fit a curve, though. What I'll get it to do now is to plot 2 separate lines, one using the left-hand group of 6 points, there the turkeys less than 15 pounds, and another line for the rest of the points for turkeys weighing more than 15 pounds. You can see that the left-hand line does slope more than the right-hand line. You can imagine that if we had data for smaller and smaller turkeys, we would get lines that got steeper and steeper. In fact, over the whole range of weights, we wouldn't be dealing in straight lines at all. We'd actually have a curve, and the curve should pass through the origin. If that's true, then it presents us with a more complicated mathematical problem.
Well, let's suppose the graph of our function is indeed a curve. Since the graph looks like this, then according to what you've seen earlier in the unit, it could be the graph of a power law T equals kW to the n, where k and n are constants. And in fact, for the slope to decrease as we move from left to right, we'd need to have n less than 1. Well, as you know, the way to test for a power law is to draw a log-log plot. I've already done this for our data, and here's the result. A graph of log t against log w. And I think you'll agree that this straight line is a pretty good fit to these points. And that means we do have an approximate power law connecting t and w. Now you know from the unit that this straight line can be used to find the particular power law that we're after. To do that, I need the slope of the line and the coordinates of any one point on the line. Well, drawing in a triangle, like this, that is 2 units that is about 1.33 units. So the slope is 1.33 over 2, which is 0.665. And for the 1 point on the line, I'll take log W equals 3, for which the other coordinate is 5.55. Now let's apply that information to find the values of k and n in the power law T equals kW to the n. Taking logs on both sides gives log T equals n log W plus log k. In other words, n is the slope of the line on the log-log plot. So we have n equals 0.665. Then log k is equal to log t minus n log w, which is 0.665 log w. So using the coordinates I read off the graph, log k equals 5.55 minus 0.665 times 3, which is 3.56 to 2 decimal places. Well, log k is 3.56, so k itself is e to the 3.56, and I can work that out. It's about 35. So our conclusion from the log-log plot is that the data are quite well fitted by the power law T equals 35 W to the 0.665. In fact, I've drawn the graph of T equals 35W to the 2/3 superimposed on our original data points. You can see that this model also gave a reasonable fit to the data. So what does our model predict for a 20-pound turkey? I can read the time straight off this power law graph. It's about 260 minutes. So our model says that after 4 hours and 20 minutes, the turkey is safe to eat.
Well, my turkey's been cooking for about 4¼ hours now, so there should just be time, before I look at it, to summarize what we've been doing in the program. I find it useful when I'm thinking about mathematical modeling to break the process down into a number of separate stages. This gives a useful framework for thinking about mathematical modeling, and we shall use it in all the later television programs in Block 5, and sometimes in the units, when we're dealing with a model rather than a piece of mathematics. Let me introduce this framework now and describe its various stages in relation to the turkey cooking problem. There are 7 stages in the process, and I've laid them out like this. I'll describe them one at a time in the order one goes through when one tackles a modeling problem. Mathematical modeling is about using mathematics as an aid to solving real problems. Most real problems are stated in a rather imprecise way, and usually in a non-mathematical way. The first thing one has to do is to specify the real problem. We started off the program by talking about this particular turkey that's in the oven now, and we asked how long it would take to cook. But the problem that we've actually tackled is a more general one. Find a way of determining how long it takes to cook a turkey of any given size. In the course of making the problem precise, we had to decide exactly what we meant by some of the terms we used. When is a turkey cooked? For the purposes of the model, when it's reached a temperature of at least 85 degrees centigrade throughout. What do we mean by size? In this case, weight is the most useful measure of size. Now, once you're sure precisely what problem you're trying to solve, you want to begin to translate it into suitable terms so that mathematics can be brought to bear. We call this part of the process setting up the model. At this stage, one has to choose some variables and formulate a relationship between them. We used cooking time and weight as variables. In the course of specifying these variables, we made some simplifying assumptions. For example, we assumed that the oven temperature would be fixed, though we could have taken that as a variable as well, but at the cost of making our model more complicated. Another simplification we made was that the turkey's weight truly summarizes all the different characteristics of the turkey which might affect its cooking time. To establish the relationship between cooking time and weight, our first step was to decide to use an empirical method, and that meant collecting some data. We also had to make an intelligent guess as to what form the relation might take. And our first assumption was that it would be a linear one. And now at last we'd formulated our mathematical problem. The problem was simply to find the best straight line fit to the given data. Solving that problem was easy enough. We fitted a line, or rather, the computer fitted a line and told us its equation. So, now we'd solved the mathematical problem, and you might have assumed that that was the end of the matter. But it wasn't, of course. You see, we started off with a real problem, given in non-mathematical terms, and we had to express our findings in the terms of the original problem. Interpreting the solution, in our case, meant saying what it had to do with cooking turkeys. But we still weren't finished. It's a golden rule in mathematics, always to check your solution to a problem, if you can. Since we were dealing with a real problem, this meant asking whether the solution made sense in real terms. We call this, rather grandly, comparing with reality. In cookery, it's a question of the proof of the pudding being in the eating. So we can't finally compare with reality until the turkey actually comes out of the oven. But a partial check was provided by the fact that our results did appear to agree, more or less, with the kind of information that we got from the cookery books. So it looks okay, at least, for turkeys of normal sizes. But in another sense, we compared our results with reality and realized that something was wrong, because they suggested absurdly long cooking times of very small turkeys. And at this point, we went through several steps of the modeling process again. We modified our model by changing it to a power law. This led to a different mathematical problem, to find the power law explicitly, which we solved by using a log-log plot. And that's an important point about modeling. It's very rarely a once-and-for-all process. More often than not, it's iterative. You start with a simple model, and you think of ways of improving it. This may involve several trips around this loop. Finally, when you've done your modeling, you generally have to tell somebody about it, either by writing a report or by talking to them, just as I'm telling you now about the turkey problem. Well, sounds as though I ought to take a look at that turkey.